Let's go over our practice on electron configurations now. So we can see our table up above, and this kind of summarizes what we spent the last little while talking about. So let's look at the first energy level. How many subshells does it have? The subshells are another name for the various orbitals, the s, p, d, and f. And we know that at the first energy level, there can only be one type of subshell, the 1s. How many total orbitals? Well, there's only one of each type of s orbital, so there's only one, and each orbital can hold 2 electrons. The second energy level has 2 types of subshells, s and p. How many total orbitals? Well, there's 1 2s plus 3 2p is 4 total orbitals, which can hold a total of 8 electrons. At the third energy level, we add the d. So there's sp and the d orbital. There's 5 d orbitals at each level, so we now have 9 total orbitals, can hold 18 electrons. And finally, the fourth energy level, that adds the f orbitals, so we have s, p, d, and f. We have 16 total orbitals, 1s, 3 p's, 5 d's, and 7 f's, and 32 electrons. So now let's look at nitrogen. How many electrons does nitrogen have? Well, we go to the periodic table, we find it has 7 electrons. And so it's going to use the 1s, the 2s, and the 2p. Configuration, 1s2, 2s2, 2p3. For these next ones, we should start out by looking at a periodic table. So I'll assume that you have one nearby that you're referring to. And the next thing that we're going to do, or I should say the first thing that we're going to do, is identify the number of electrons for each of these elements. So magnesium has 12, chromium 24, palladium has 46, antimony has 51, oganesson has 118, and arsenic has 33. So let's do the electron configurations. Again, we start 1s2, then 2s2, 2p6. That's a total of 10 electrons, and we need 2 more, which gives us 3s2. Alternatively, we could use the shorthand notation and take the noble gas before magnesium, which is neon, and then just add in the valence electrons for 3s2. Chromium, again, we just start lowest energy and work our way up. Remembering though that when we get to d orbitals, which we will here, that 4s comes before 3d. Again, we can also do this as the shorthand. Again, we use the noble gas that comes closest to and before the element. Which would be argon, followed by 4s2, 3d4. Now it's these next couple examples that will illustrate even better why this shorthand is important. And I'm going to jump down to oganesson to show that. So if we did the full configuration for oganesson, it's going to look like this. So after 6s, that's when we jump back to 4f. Finally, 7p6. So you can see there's a lot to remember there. And once you've gotten used to these, you won't necessarily find that one like that is hard. It's just very, very time consuming. And so much, much easier if we can just take the noble gas that comes before it, which is radon, and then just list the last row. So for our remaining examples, we're just going to stick with the shorthand. Palladium and antimony are going to be very, very similar. Why will they be similar? Well, they're in the same row. So if we're using the shorthand, they're both going to start with krypton. And I'm just going to bring them down here so I don't try and stick too much in that same space. Both of these will start with krypton though. And again, all we need is what comes after that. So for palladium, that's 5s2, 4d8, and for antimony it goes a little bit further. 4d10 and 5p3. Finally, arsenic uses argon as its starting point, and we get 4s2, 3d10, 4p3. Now, how do ions affect this? So we should hopefully remember an anion is a negative ion, and a cation is a positive ion. Well, remember for ions, we change the number of electrons. So if we have sodium plus, how will that be different from sodium? Well, sodium, we could do its configuration 1s2, 2s2, 2p6, 3s1. And that's because it has 11 electrons. But if it's sodium plus, that means we've lost an electron. And instead, we have only 10 valence electrons. Which one goes away? Well, it's the highest energy one. And so we get 1s2, 2s2, 2p6. That 3s electron is the highest energy electron, and that's the one that gets lost when it loses an electron. What about if we have an anion, as we do in I-? So iodine normally has 53 electrons. If it's an anion though, we're going to add electrons, so we have 54. So in other words, I- has the same configuration as xenon. And then finally, the last one of that group is calcium 2+. So calcium 2+, calcium has 20 electrons. So if it's a +2 charge, then we're going to be down to 18 electrons. So the last thing we want to do here is identify the number of valence electrons in each of these elements. And if you'll look carefully, you'll see that most of these are the same ones that we just did the configurations for. So to remind ourselves, what is a valence electron? Again, a valence electron is one of the electrons in the outermost shell. So for magnesium, if we recall its configuration, magnesium's configuration ended at 3s2. So only those 3s2 are valence electrons. The other ones, the ones at the 2 level and the 1 level, are at a lower energy level. And so those are not valence electrons. Only the 3s is a valence electron. So for magnesium, we would have 2. And as we also indicated before, you can just follow right on the periodic table with the columns. Arsenic has 5, 4 for carbon. Antimony, being in the same column as arsenic, also has 5. Oganesson is in the noble gas group, group 18. All of those have 8 valence electrons. And then these last 3, sodium, normally has 1 valence electron because the 3s is its highest electron. But once we get rid of the 3s, then there are no electrons in the third energy level. And so our highest energy level in the sodium cation becomes the 2 level. And so that has 8 electrons. I- has 8, and calcium 2+ also has 8.